From the phone in your pocket to massive energy grid installations like these containerized units, every lithium-ion battery has a strict expiration date. This diagram shows the difference between two critical metrics. On the left is state of charge, the temporary energy your battery holds today. On the right is state of health, the permanent overall capacity that shrinks over time. That shrinking process accelerates when the internal chemistry is pushed outside its optimal comfort zone, known as the safe operating area. To stabilize battery health, you must carefully balance three strict boundaries: temperature, total charge capacity, and charging speed. Keeping the battery within these three limits is the only proven way to significantly extend its permanent usable lifespan. High temperatures break down battery chemistry faster than any other factor. During normal operation, a thin, protective chemical barrier called the solid electrolyte interface, or SEI, naturally forms over the surface of the battery's internal electrodes. But when the battery gets too hot, this protective barrier grows out of control. It acts like a parasite, consuming the materials the battery needs to function. As this diagram illustrates, lithium ions try to move back and forth between the electrodes to create power, but they get trapped inside that overgrown boundary. This permanently increases the battery's internal resistance, starving it of available energy. Keeping your devices cool actively prevents this chemical layer from suffocating the cell. The second major threat comes from leaving a battery fully charged or completely drained. When pushed to maximum capacity, you force millions of lithium ions into the active materials, causing internal particles to physically swell and expand. Leaving the battery pegged at 100% locks those swollen particles in a state of unrelenting physical tension. Looking at this diagram, you can see how this mechanical stress forces the particles to crack apart. Once fractured, these pieces can no longer hold a charge, permanently reducing the battery's total capacity. By avoiding the extreme edges of capacity, you prevent the internal components from physically shattering. The third boundary is speed. Pumping electricity in too fast, especially when the battery is cold or nearly full, creates a massive bottleneck. During a charge, lithium ions must physically absorb into the negative electrode. That intercalation process takes a specific amount of time. During fast charging, ions flood the electrode faster than the material can absorb them, causing a massive pileup. This creates lithium plating. The ions fuse into jagged metallic structures that block the surface, permanently destroying that battery's capacity. Pushing electricity into a device faster than it can be processed directly converts usable energy into dead metal. To prevent these three extremes on a large scale, electric vehicles like this Nissan Leaf rely on complex software to protect their cells. This software is called a battery management system. It acts as the brain of the battery, constantly adjusting voltage, temperature, and current to strictly enforce that safe operating area. Smartphones and laptops we use every day contain miniature versions of this management system. When you enable features like optimized charging, you are giving that system permission to hold your battery at 80% overnight, avoiding high-tension states and minimizing heat. And when you have the time, using a standard speed charging block instead of an ultra-fast charger gives the ions enough time to absorb properly, avoiding those metallic traffic jams. Every single lithium-ion battery will eventually degrade. But by keeping the chemistry cooler, the charging gentler, and out of the extremes, we can dramatically extend how long they actually last.